Hello, everybody, and welcome to week 2 of Math 1220 online. I have just a couple of announcements to make before I say a little bit about the math this week. So I just want to point out that exam scheduling is now available on Canvas. So if you log into Canvas, you can click the Schedule Exams link on the left menu, and there you can schedule when you're going to take each of the exams in the proctoring center. You don't have to schedule them all now, but you can get started scheduling them. In particular, you'll want to sometime before week 6 schedule when you're going to take your first exam. So week 6 is that week between February 13th and February 17th. Most of you will want to schedule in the Marriott Library proctoring center. They're open 9 to 5 Monday to Friday, but again, you have to schedule a time in advance, and times do fill up, so make sure you do schedule a time. And then there's some other options. For example, if you need to do it in an evening time, you might try the Sandy Testing Center, which has some evening times Monday to Thursday. And if you're outside of Salt Lake City, you can also arrange, for example, to do proctoring at a library. So you can look in the syllabus for a little bit more about this, what your options are. And you can look at sort of the schedule exams page for a little bit more about what your options are here. And I will sort of remind you about this and say a little bit more about this as we get closer to that first exam week. And feel free to reach out if you have any questions. Okay. The other big thing logistically is just remember that this week you have both a web work and a written assignment due on Friday at 11:59 p.m. So the first week of the class, we just had that web work demo assignment. There was no written assignment. This week, you do have a written assignment due as well. And as a reminder, if you go to the written assignment page, you turn that in on Gradescope. So you sort of print out the worksheet, fill it in, and turn it on Gradescope, or you can fill out the worksheet just like on an iPad. But go ahead and look at that and make sure you understand how to submit it. Okay, so what are we doing mathematically this week? Well, it's section 6.1 through 6.4, but the real mathematical goal is to understand what we really mean when we say like a to the b. So here, this is like for a, any positive real number, and b, any real number. And this is something you've probably worked with before, like in algebra classes, and in algebra classes, or maybe in a calculus class, if you took a calculus class outside University of Utah before this, you might have sort of worked with these things already. But sometimes it's actually a little bit tricky to make precise what a to the b means. Well, in some cases, it's pretty clear. Like if I look at 2 to the 7/11ths, well, that really just means take 2 to the 7th power and then take the 11th root of that. And more generally, like if I take a real number and I raise it to a rational number. So a rational number is something that's just a quotient of 2 integers, the fraction, with sort of whole number, numerator and denominator. I can sort of make sense of it like this. I take some power and then I take some root. And that's all well and good. But what do I mean when I say like 2 to the pi? I mean, pi you can't express as a fraction like this of 2 whole numbers. So you can't sort of think of it as taking some power then taking some root. You need some other way to understand it. So one way you could do that, you could say, well, I can sort of write pi as 3.14159, so on and so on. And then I can sort of make sense of like approximations of pi, like saying like pi sort of has this expansion, saying like if I want to sort of get close to it, like if I want to get within 1/100th, within 1/100th, let's say I should take 3.14. If I want to get within 1/1000th, I should take 3.141. And so if I like cut off the, if I just like look at 3.14, like 3.14 is 314 over 100. So that is a fraction. So I can make sense of like 2 to the 3.1 or 2 to the 3.14 or 2 to the 3.141 because that's just raising 2 to some fractional power. So I can do that by like, so 2 to the 3.14 would be 2 to the 314, and then I take a 100th root of that. So sort of this process makes sense. So one way I could like try and define 2 to the pi is I could say, well, these approximations should be getting better and better. And like sort of as I go further and further out, like these approximations somehow approach some real number, some type of limit, and I should call that number 2 to the pi. And it's true you can actually proceed in that way. Like you can sort of make that a rigorous definition. You can work out carefully what that means. You can show sort of such a thing exists, and we're to define the number a to the b, like any number a to the b, where a is a positive number and b is any real number. But somehow that's not actually the easiest way to do it. If you want to sort of define what you mean by a to b, there's a better way sort of using calculus, but it seems a little bit funny the first time you look at it. But here's our calculus to rescue, and that's sort of what we're going to do, what we're doing this week. So somehow you sort of you proceed backwards from the order you would normally proceed, like in like an algebra class, like algebra 2 or something, high school algebra, college algebra. So like in college algebra, like first you would define like powers, and then you would define logarithms, and you sort of understand properties of powers and logarithms. You sort of define logarithms to like be the things that undo taking powers. But actually, sort of when you do that, like somehow, unless you're very careful, you haven't actually sort of defined in a good way powers. So what we actually do is we go in the opposite direction. First, we sort of define what we mean by natural logarithm, so ln. We sort of give a definition of that has nothing to do with exponentiation. Like we just define this actually using integration. So that's sort of the key thing in 6.1. We just sort of define a function that we're going to call the natural logarithm using integration. And this definition by integration makes it easy to show like it satisfies some basic expected properties. For example, like the logarithm of the product is the sum of the logarithms. Once we have defined the natural logarithm, then we're going to define e to the x to be the inverse function of the natural logarithm. So this is sort of the opposite of how you might have seen it before, like where the natural logarithm is defined to be the inverse function of e to the x. Like somehow like the easier way to do it is actually first define what you mean by natural logarithm, and then define e to the x to be the inverse of that. So once you have that, then sort of like the simple properties of the natural logarithm will also sort of translate into the standard properties of e to the x. So for example, like e to the x times e to the y is e to the x plus y. So this identity sort of matches with this one. Good, and so, well, so that's sort of the idea. Of course, in order to do that, we have to sort of learn a little bit about inverse functions, and in particular, how we can sort of think about inverse functions when we're doing calculus. And so that's what's covered in 6.2. And then section 6.3 does this sort of introduces e to the x, which we also call x of x. Okay, and then finally, once we have all that on the table, we define a to the x for sort of an arbitrary positive real number, a, to be e to the natural log of a times x. And sort of that is something that now makes sense. The reason a has to be a positive real number is because the domain of natural logarithm is only going to be positive real numbers. So for ln of a to make sense, we need a to be a positive real number. Okay, so this is what we'll define, and then we can check. So once we have this definition of a to x, we can actually check that this agrees with the obvious definition using powers and roots when x is a rational number. So you can check, sort of using the properties we've established so far in 6.1 through 6.3, that like sort of this definition of, so if I wrote like 2 to the 7 over 11, well, if I sort of adopt this definition, then I get e to the ln of 2 times 7/11. And if I sort of adopt sort of my initial interpretation, I get 2 to the 7th, and then I take an 11th root. And so we want to, and just to make sure we haven't done anything crazy, we should check that sort of that these two expressions really agree. So that sort of this notation sort of makes sense with what we already understood by this notation. And that's sort of a part of 6.4. Okay, so let me just highlight, I mean, some of the advantage of this approach, sort of compared to like trying to find sort of powers by sort of this approximation process, is that, well, one, when we do it, sort of we can quickly sort of establish the basic properties of these functions. In particular, sort of this is really point 2, in particular, we can understand the calculus properties of these functions. So when we define it this way, like starting with integration, well, when we have integration, we can sort of use the fundamental theorem in calculus, compute the derivative. Since we're starting with calculus, like we can naturally sort of compute the derivatives of all these things. And that's sort of well, this is a calculus class, like when we use these functions, we don't want to just use these functions. We also want to understand like how to do calculus with these functions. And so that's sort of built into this approach. Okay, well, enjoy this week, and hopefully I'll see you in office hours.